Okay, now let us start with the first part. We're taking up chemical properties of haloalkanes or halogen compounds. Now, there are three basic types of chemical properties that we need to know. The first one is like substitution reactions. Second is elimination reactions. And the third is reaction with metals. Now, these are the three basic types of reactions that we have. And the first category of reactions, that is substitution reaction, this is something which I am going to start with. So first of all, we would take up substitution reactions. And substitution reactions are in general shown as SN type of reactions, right? So these are basically SN type of reactions. Substitution reactions, they can be of many different types. So the common types that we have to, undertake in this chapter: SN1, SN2, SNI, and SNAR. See, of all these, SN1 and SN2 would be discussed in detail. SNI as such, there are very few reactions which go through SNI mechanism, and SNAR are also quite less. So, but we would be talking about all of them. However, SN1 and SN2, we would be taking up in detail. First of all, let me give you a general method or a general type of substitution reaction. So in any substitution reaction, you always, start with Rx, where X is more electronegative and attains a partial positive charge, and this would attain a partial, carbon would be partial positive and halogen would be partially negative. And this can be treated with a nucleophile. The nucleophile attacks the carbon because it is positive, and nucleophile is always, your electron-rich component, right? And the product is like the nucleophile making a bond with carbon, and halogen is separated. As you can see that in this general type of reaction that I have shown, right, there's something which you have to understand, that in such a reaction, there is one electron-rich component moving in, and there is one electron-rich component moving out. As you can see, the general category of this, you can see that one electron-rich component moves in, and another electron-rich component moves out. So basically here, we say a stronger nucleophile replaces a weaker nucleophile. A stronger nucleophile replaces a weaker nucleophile. That is what we have here. So these are called nucleophilic substitution reactions because they are initiated by a nucleophile. So they are called nucleophilic substitution reactions, SN reactions. Okay. X is also referred to here. X is also referred to as a leaving group. So X is also called a leaving group. So this is a general format. the first thing you have to know before you start with this is to understand the strength of nucleophiles. Now, when it comes to, one nucleophile getting replaced by another, and I did say that a stronger nucleophile replaces a weaker nucleophile. In other words, you have to know which nucleophile is stronger and which nucleophile is weaker. Or in other words, you have to know the strength of nucleophiles. Along with that, you also have to know which groups are good leaving groups and which groups are not good leaving groups. First of all, let us start with the strength of nucleophiles, okay? So, first of all, just checking out whether everyone is admitted or not. Yes, I think fine. So, going back to the work, yeah. Let us start now. We first of all understand, how to decide which nucleophile is strong and which nucleophile is weak. So we're doing strength of nucleophiles. See, there are various ways in which strengths of nucleophiles can be decided. One of the theoretical procedures which you can use, which has been described in most of the books, I am going to teach you. But then later on, as we take up examples, I am going to show you how the strengths can be decided when nucleophiles don't fall into the normal groups that you have done, right? So when you have some weird nucleophiles being compared, how do you decide the strength? That also we should discuss, but that could be later on. First of all, just understand the rules, right? The basic rules. Okay, let us start with the first rule. First of all, let us take up the factors which decide the strength of nucleophiles. The factors which decide the strength of any nucleophile would be the charge of nucleophile, the basicity of nucleophile, which is very important, solvent used in which the nucleophile is reacting, and fourth, it should be the size of nucleophile, which is also at times important. Before we start with this, I have already done this with you, but let me revise you the basic definition of nucleophiles. What are nucleophiles? These are electron rich. These are electron rich attacking reagents. They attack the reactant. The reactant is also called a substrate. So they attack the substrate, right? And they are electron rich. They can be either negative or neutral. Some of the negative nucleophiles, Cn minus, OH minus, X minus, etc. X stands for halogens. Some of the neutral nucleophiles, you have H2O with 2 lone pairs. Oxygen is the donor site. Every nucleophile has at least one donor site. In Cn, carbon is the atom through which electrons are donated. Nitrogen can also do that, but then carbon, generally carbon is preferred. Here oxygen and here halogen. Here again oxygen. These are called donor sites. In ammonia, it is nitrogen, right? So these are all, different neutral nucleophiles. So nucleophiles are basically electron-rich attacking reagents. They generally attack the electron-deficient part of the substrate. The part which is most electron-deficient, many a times also shown as, shown by a plus delta sign, Now that is the part of substrate which is electron deficient. So any nucleophile would attack the electron deficient part of any substrate, the part which has partial positive charge. Okay, now let us take up how to get the the factors, and based on that, how do we decide the strength? So we go back to our factors. The first thing, right? Let us take up the first thing. Charge. We say that any nucleophile with negative charge is always stronger than the neutral nucleophile. So negatively charged nucleophiles are stronger than neutral nucleophiles. This is in general given. The best examples could be, you can take up OH minus and compare it with its conjugate acid, which is H2O. OH is always stronger. You can take SH minus, which is always stronger than its conjugate acid, H2S. Or you can take NH2 minus, which is always stronger than its conjugate base, NH3. So I think these are all different nucleophiles, which are compared. Negative nucleophiles are always stronger than the neutral nucleophiles. This is the first important thing. The second important parameter is basicity. So the first thing you look at a nucleophile is figure out whether it is charged or not. And if it is charged, then maybe the negatively charged nucleophile is stronger and the neutral nucleophile is weaker. That is how it goes. Just a moment, I'm just coming back to you just to figure out if everyone else, if no one has, internet problem. Now, I think everything is perfect. Basicity. Now, when you check the basicity, this is also a very primary factor. Here there are two options. One, when nucleophiles are from same period. When nucleophiles are from same period, let's see what happens. When nucleophiles are from the same period, we find that basicity always is directly proportional to nucleophilicity. In fact, I could have written it the other way around, because we are checking the strength of nucleophiles. I could have written it as nucleophilicity is directly proportional to basicity. Here I can give you some examples, right? Examples could be going from, you can see CH3 minus, where donor atom is, carbon, is greater than NH2 minus, greater than OH minus, and greater than F minus. As you can see that there are donor atoms from the same group. So when here you find that the donor atoms, when they are from the same group, nucleophilicity is same as basicity. It is very simple to know the basicities. You find that CH3, the conjugate acid is CH4. I'm talking about conjugate acids. CH4. The conjugate acid here is NH3. Conjugate acid here is H2O, and conjugate acid here is HF. The strongest acid amongst this is HF, which is more acidic than water. Water is more acidic than ammonia, and ammonia is more acidic than CH4, because in CH4, hydrogen is connected to carbon, the least electronegative element amongst all of them. You know, fluorine, oxygen, nitrogen, and carbon. What is most electronegative? Fluorine. And what is least electronegative? Carbon. So with carbon, when hydrogen is attached, it cannot be easily removed. So this is the weakest acid. Because this is the weakest acid, its conjugate base CH3 minus should be, you know, most basic. So when a conjugate acid is weak, the base is supposed to be very, very strong. So acidic strength goes like this, but the, you know, the basic strength is exactly opposite. This is one way of finding out, you know, the nucleophilicity. However, in general, what you could do is, when donor atoms are different, you can even check the electronegativity of the donor atom in general. Electronegativity of donor atoms, right, generally is inversely related to their respective nucleophilicity. Carbon is least electronegative amongst all of them, nitrogen, oxygen, or fluorine. And that is the reason why carbon is able to give away electrons most readily. So lower the electronegativity, higher is the tendency to give electrons, and hence higher is the nucleophilicity, right? So that is also one way of deciding the nucleophilicity, right? Based only on the donor atoms, when the donor atoms are different, right? So this is one way of doing it. Generally, this kind of comparison is valid for both, you know, in any kind of solvent. So this is like valid for any solvent. Okay. So this was about the basicity, which is observed for elements when the donor, or for donor atoms which are from the same period. We say going from left to right in any period, nucleophilicity decreases. That is what it means. As you have seen here, going from left to right, the nucleophilicity decreases. Clear? What about when nucleophiles are from the same period? When nucleophiles or donor atoms of nucleophiles are from same group. So when they are from same group, things are largely dependent on the nature of solvent. The nature of solvent. So in that case, solvent plays a very important role. So the first case is, there are two basic types of solvents: polar and protic solvents. And P, it is polar and aprotic solvents. Before we take up what exactly are polar protic and polar aprotic solvents, I am just going to give you some examples of polar protic and polar aprotic solvents. So just moving on to that next page and just giving you an idea about what polar protic and polar aprotic solvents are. Let's say this is water. Because oxygen is more electronegative, hydrogens are partially positive and oxygen partially negative. So water is polar. And water also has hydrogen connected to one of the very strongly electronegative atoms, and hence this hydrogen can be easily lost as H+. So water can also give away H+, or water can also produce H+. So any solvent which can produce H+ is a protic solvent. So this is polar and protic. Another example of polar and protic would be any alcohol. This is polar and protic because, again, the same thing. This is minus and this is plus. So these are polar and protic solvents. Whereas if you take up CH3, C double bond O, and CH3, this is acetone. It is polar because you have your oxygen remaining partially negative and carbon remaining partially positive. That makes it polar. But there are no hydrogen atoms directly connected to oxygen or any other electronegative atom. All the hydrogens are connected to carbon, but carbon is not very electronegative. So any hydrogen cannot get separated out from CH3 as H+. That's because the electronegativity of carbon is not so high to pull both the electrons from any covalent bond and release H+. It is impossible. And therefore, or it is very difficult, in fact. So acetone would, it can be a polar solvent, but it would not release H+. So we call this as polar and aprotic solvents. It comes under the category of polar and aprotic. I can give you some more examples. This is called dimethyl sulfoxide, DMSO. And then we have this, dimethyl formamide, but before that, CH3C triple bond N. This is called acetonitrile, also a polar and aprotic solvent. And then there is one more, which is so important that I need to mention that. This is dimethyl formamide, HC double bond O, N, CH3 and CH3. This is called dimethyl, common name, formamide, also known as DMF. These are all polar and aprotic solvents. These are the commonly used polar and aprotic solvents. There can be many more, but these are the common ones. So first of all, you have to know what these polar protic and polar aprotic solvents are. Those solvents which are polar and can release H+, they are protic, polar and protic. Those which are polar but cannot release H+, they are polar and aprotic. I hope you've got this. Now coming back to our work. See, when you are comparing nucleophiles or donor atoms of nucleophiles, if they are from the same group, then the order of nucleophilicity would be decided by solvents. In polar and protic solvents, nucleophilicity is inversely related to basicity, which means you may have something like this. Okay, so if you compare the nucleophilicity of things like F minus, Cl minus, Br minus, and I minus, all from the same group. It is very simple. You may say, yeah, what is the conjugate acid of F minus? That is HF. And you know that if you compare the corresponding acids, conjugate acids of all of these, HI is the strongest and HF is the weakest. Because HF is the weakest acid, its conjugate base, that is F minus, would be a very strong base. So that makes F minus a very strong base. And here in polar and protic solvent, nucleophilicity and basicity are inversely related, which means a very strong base would be a very weak nucleophile. So in polar and protic solvents, you find that, and if the donor atoms are from the same group, if nucleophiles from the same group are compared, and if the solvent is polar and protic, nucleophilicity and basicity are inversely related. Find out the basicity, right? The one which is weakest base is the strongest nucleophile. So we have this, okay? So that's the first thing that we have, and you all have to know this. This is the first order that I have given you here. Know this order properly, right? Coming back to the next part, and that is polar and aprotic solvents. Now, polar and aprotic solvents, things are different. Nucleophilicity and basicity are directly related. And therefore, the order here would be F minus is greater than Cl minus, which is greater than Pr minus, greater than I minus. Why? Because F minus is the strongest base. And why F minus is the strongest base? Because its conjugate acid HF is the weakest of all halogen acids, right? So of all the comparable halogen acids, HF is the weakest. So that is what makes F minus the strongest base. And in polar and aprotic solvents, F minus would also be the strongest nucleophile. So this is a general way of finding out which nucleophile is strong and which nucleophile is weak. What we have here is, for polar and aprotic solvents, and yeah, so very simple to make you all understand that basicity of any nucleophile is a very important parameter for deciding its strength. Here you have to know whether nucleophiles or the donor atoms in nucleophiles come from the same period or from the same group. If they come from the same period, it is as simple as nucleophilicity parallels basicity, or nucleophilicity is directly proportional to basicity. However, if you find that your nucleophiles or the donor atoms of nucleophiles are from the same group, now in that case, the strength of nucleophile would be largely dependent on the nature of solvent used. If the solvent used here is polar and protic, a polar solvent also capable of releasing H plus like water or alcohol, we say nucleophilicity, and this is exactly opposite to what happens in periods. So going from top to bottom in a group, nucleophilicity is inversely related to basicity in polar and protic solvent. So we have fluorine minus less than chlorine, less than bromine, and less than iodine. Why? Because F minus is the strongest base, and therefore it is the weakest nucleophile, as they are inversely related. But the same taken in polar and aprotic solvents, you find that nucleophilicity and basicity are directly related. I have given some examples of polar protic and polar aprotic solvents, which you can note down. So if you consider the factors which we have for deciding the strength of nucleophiles, we've considered charge, we've considered basicity, we've also considered the solvent and the importance of solvent in deciding the strength of nucleophile based on its basicity. So these three parameters have been discussed. There's one more which is left, and that is the size. Here I'm going to put size, and let us understand what this means. So the fourth parameter that we would talk about is the size. Now, size of nucleophile, the size of nucleophile is like considered only when nucleophiles are from the same family. I would give you an example. When nucleophiles are from same family, right, and have the same donor atoms, when nucleophiles are from the same family and if they have the same donor atoms, nucleophilicity is inversely related to size, which would also mean that, look at this, if you take any, first of all, if you take any alcohol, the formula is ROH, you remove hydrogen, you get RO minus. This is electron rich and is called an alkoxide, sorry. This is called an alkoxide ion. This can act as a good nucleophile, so you can use it as a nucleophile. So let us find out what would be, with all these alkoxides. All alkoxides like CH3O minus, CH3CH2O minus, CH3C, CH3H and O minus, and you have CH3C, CH3, CH3 and O minus. Now, all of these belong to the same family, that is alcohols. And here you find that this is methoxide derived from methanol, ethoxide derived from ethanol, isopropoxide derived from isopropanol, and tertiary butoxide derived from tertiary butanol. Now, if you have to compare the nucleophilicity of all of these, you have to know one important thing. They all belong to the same family, right? They are all derived from alcohol. They all have same donor atoms. And in such cases, if you have to relate the strength, you say the one which is smaller is going to be the strongest nucleophile, and the one which is bigger is going to be the weakest nucleophile. It is as simple as that a smaller nucleophile is able to reach the carbon atom of substrate more readily, whereas a bigger nucleophile, for a bigger nucleophile, it would be very difficult to reach a tetrahedral carbon for causing that substitution, because a bigger nucleophile would not be able to reach that carbon due to a lot of steric hindrance that it has. So smaller nucleophiles are more agile, they have reduced steric hindrances, and hence are able to very quickly reach the tetrahydrocarbon for causing that substitution. So, but only for such special cases that you have to consider the size. I hope this is clear to all of you all. Any other case, a case other than what rules that you have studied so far, any other case, you have to know that there are two things of doing it. The best way to do is then just check the electronegativity of the donor atom. So any other case, just check, a very simple rule, just check the electronegativity of the donor atom. So if you have two nucleophiles where the donor atoms are neither from the same period nor from the same group, where these normal rules that I have given you are not properly followed, then how do you decide everything? You decide everything only on the basis of, you decide everything on the basis of electronegativity of the donor atom. Yes, Manav has moved out, so I'm just... Manav, you're in. I think there's one more person who has who's not there. I don't know who has lost the connection. Please, the moment you move out, please message me, right? Because if you don't message me, I may not be able to figure out, whether you are out or not, or whether I have to admit you or not. So please give me an SMS. The moment I receive SMS, I would admit you. Okay. So there's someone else also, who's moved out. I don't know how. And I hope you have understood all of this, because this was such an important thing, right? I'm going back to that. So this was such an important thing, right? The strength, they have been discussed. There are quite a few questions in our worksheet where strength of nucleophiles have been compared. Some very odd questions also asked. I would give you the numbers of all those questions, because normally Sundays we would also discuss the MCQs. So all good MCQs from the worksheet would be discussed. So I hope you have understood all of it. This was about how to decide the strength of nucleophiles. First, charge, then basicity. Basicity when donor atoms are from the same period. Basicity when donor atoms are from the same group. In same period, basicity and nucleophilicity are the same, whereas in groups, right, in polar and protic solvent, nucleophilicity and basicity are reversed, and in polar and aprotic solvent, nucleophilicity and basicity are the same, directly related. And if nucleophiles have same donor atoms and are from the same family, then you check the size. Smaller the size, stronger the nucleophile. In any other case, general, where you have to do comparison between nucleophiles and such a comparison would not fall into any of these rules given, the best way to do is just check the electronegativity of the donor atom. Any nucleophile in which the donor atom is more electronegative is going to be less nucleophilic. Okay? Now, if you have any questions, please ask. I am there to answer your questions. I think there are two people who have lost the connection. I don't know what has happened. Bhavya has moved out, I think. So, yeah, if you have any doubts, please ask. I am there to answer your questions, right? I'm there to answer your questions, yes. There is a small doubt given. Drishti has moved out. Oh yes. I would try to put, just wait for a moment. I would try to bring both of them back. Just a moment. Okay, I tried contacting Bhavya also, but it seems that he's not there on the phone. So I think we continue now. Drishti is in now, but Bhavya is still out. And Bhavya is in now. So there's someone else who is out. I don't know now who has gone out. But I think, yeah, anyone is still out. And I think, I don't know who. Um, Fine, we go back to our work. So the next thing, so once we've done all this, the next thing is about the leaving group. So you will, just a moment. Hello. અરે ભવ્ય મીટિંગમાંથી બહાર નીકળી ગયો હતો એટલે મેં ફોન કર્યો હતો કે એડમિટ થઈ જાય પાછો ફટાફટ. એને કદાચ નેટનો પ્રોબ્લેમ હતો કે લેક્ચર ચાલતો હતો એટલે. હા એ ના આવી ગયો લાગે છે, વાંધો નથી કદાચ. હા ખાલી એને કહી દેજો. ઓકે. Okay, so I think everyone, I think Bhavya is in, so fine. I thought he was out. So going back to this, okay, now the next thing we have to know is the, is to know about leaving groups, right? So any group is a better leaving group if its basicity is less. In other words, capacity of any group to leave is inversely related to its basicity, which also means that the most basic groups are the worst leaving groups. That is what it means. And I have given a small list of leaving groups in decreasing order, starting with R N2 plus, followed by R O SO2 CF3. This is like a very good leaving group. The leaving group is here, okay? This is your leaving group here. This is your leaving group, which is followed by R OSO2 PH, followed by R OSO2 CH3. These are all excellent leaving groups here, right? After which you have some Ri greater than RBr. These are again two good leaving groups. And this is all based on the strength of the conjugate acid. An acid which is strong, the base which is the conjugate base would be weak, and if conjugate base is weak, you find that it would be a good leaving group. So this is followed by ROCOCF3, followed by ROH2 plus. So these are all once again leaving groups greater than RCl, greater than RF, right? And after which you have ROCOCH3 greater than ROH greater than ROR. So I'm just putting down. And finally, you have RH, where H is one of the worst leaving groups you have. So this is a general order to decide the leaving capacity of any group. And many a times they ask you such questions where you have to compare the capacities. If anything falls out of this order, then you can always decide based on basicities. Any group which is a stronger base is a poor leaving group. That is how you decide. So I think this is perfectly done. Now you have understood what leaving groups are and what nucleophiles are and how do you decide your strengths, right? I'm just going back to you to just ask you if you have any doubts. If you want to ask anything, I am there to answer, right? If you want to ask anything, you can always ask. I am there to answer. right? And if not, then I may go forward with the next part. Yes, there is a doubt. So screen rakjo. Yeah, but you already have everything in the notes. I have already sent the notes to you, and this is the notes, right? Everything is given. I have given everything. So I'm just explaining you the notes that I have written, and that's it. So I think if it is okay if you, sorry, it is okay if you just, just go through this. This is just an explanation that I'm giving you. I'm just summarizing everything and giving it to you all, okay? Done? So don't worry, you have everything in it. Right, Param? Everything is given, so don't worry. I'll tell you what to write as and when, if something is not given in the notes, I would ask you to write, okay? Now, going back to the next part now. So after having understood what leaving groups are and what nucleophiles are and how do you decide their strengths and everything, let us go back to substitution reactions. 4 different types of substitution reactions that we have. The first one that we take up is the SN2 reaction. This is called substitution nucleophilic bimolecular. So this is what we have now. Substitution nucleophilic bimolecular, also called SN2. All right. Something what we have here. Let us start now. See, first of all, this is a reaction which takes place in a single step. So there are no intermediates. These are all highlights. This is the first thing, no intermediates, right? It takes place in a single step and there are no intermediates. Second, a transition state is involved, which is highly unstable. All right. The next thing here, we find that simple alkyl halides like methyl halides or primary alkyl halides prefer undergoing such substitution. So single step, no intermediates, only a transition state, and more preferred by methyl or primary halides. Okay, let us take up one such methyl halide and let us take up its substitution reaction. Okay, let us try doing that. Okay. This is, let's say, our methyl bromide, where bromine is the leaving group, right? It is a better leaving group than OH. These are the two bonds in the plane. This is the bond coming towards us, and this is going behind the plane of paper, right? So let us take up. This is hydrogen, this is hydrogen, this is hydrogen. And you have the incoming nucleophile OH. Now, when OH and you know, this carbon is partially positive, and this is the best possible way of you know, OH to reach that positive carbon is to pass through this you know, cavity between the three hydrogens. See, if you visualize this, these three bonds would be like three pillars of a pyramid, right? The triangular base, right? The three pillars of the triangular base, and there would be some, you know, there would be a path by which it can enter. And, you know, between these three bonds, there is a lot of gap, right? And that is where OH minus would enter, right? So let us put this here. This is something which happens here. And now we reach a transition state. Now what happens in transition state? Carbon is in a very, very bad shape. This is the OH. This is the normal hydrogen. This is the bond coming towards us. And this is the bond which goes behind, right? And we have this, you know, this is our transition state. So what is the hybridization of this carbon? We may say it is sp2 because this bond is half formed and this bond is half broken. So these are not considered for hybridization. But then, as you can see, the carbon has become pentavalent. This is not really making 5 bonds, but there are 5 electron cloud surrounding this carbon. And carbon doesn't have enough space to accommodate all these 5 electron clouds. And that is what makes this carbon very, very unstable. So this structure, the transition state is extremely unstable for one simple reason. This carbon has a lot of electron, a huge electron density around it. You know, it doesn't have enough space to accommodate the electron density that it has around it. So basically, you know, this is a transition state and this carbon is extremely unstable. Now, quickly, the product gets formed, and if the product has to get formed, you know, what happens is the bond between OH and carbon strengthens, and the bond between carbon and bromine breaks. So, and all of this takes place simultaneously. So it's a single step reaction where one side the bond gets formed, the other side the bond gets broken. Bond formation and bond breaking would occur simultaneously. That is one thing. So one of the, you know, key things about this reaction is that it is single step reaction where bond formation and bond breaking takes place simultaneously. Okay. Another important thing that you have to know is, like, look at this. You started with one configuration and the product has the entire configuration flipped onto the other side. We call this as inversion. SN2 is always followed by inversion. This is one of the key things that happens in SN2. So a few more things about SN2. One, reaction is followed by inversion. Reaction is followed by inversion, which is a very, very important thing. Second, bond breaking. and bond formation occurs simultaneously. So bond breaking and bond formation would take place simultaneously. Another important thing that I have to point out here is that in such a reaction, both the nucleophile and the substrate, that is alkyl halide, both are involved in the rate determining step. What do you call this? Rate determining step is like that step which determines the rate of reaction. Because there is only one step, there is only one rate determining step. So in the rate determining step, both the reactants are involved, that is the nucleophile as well as the substrate, both are involved, which means that rate of the reaction gets affected by concentration of nucleophile as well as by the concentration of substrate, right? If any one of these concentrations increase, the rate would accordingly increase, and hence we say rate is proportional. Rate of such a reaction is proportional to concentration of nucleophile in general. I need not write OH, nucleophile, and the substrate Rx in general, which can also be given as, therefore rate is equal to K, put a constant, nucleophile and Rx. Because the rate of a reaction is determined by concentrations of two different components, it is a bimolecular reaction, or it is also called a second order reaction. Why? Because here the powers are 1, the rate would depend on 1 plus 1, that is the rate is dependent on the first power of nucleophile and first power of Rx as well. So you have 1 plus 1, 2. So you have second order reaction, which is also called bimolecular reaction, right? More about this order of reaction we would be talking in chemical kinetics, but that is why this reaction is given as SN2. 2 stands for bimolecular reaction, which also means that the rate of such a reaction depends on both the concentration of nucleophile as well as the concentration of substrate. I think this is all we have, and this was the initial part. Now, if you ask me what kind of halogen compounds would give such a reaction, then I would very easily and quickly say that this OH here, which is a backside attack, should not have a lot of hindrance. So if you have bulky groups here, suppose if you had a tertiary alkyl halide, then there would be R here, and R here. So when you have bulky groups here, the nucleophile like OH would find it difficult to move in. And if it finds difficult to move in, obviously it would not be able to give electrons. And that is the reason why it is preferred that the incoming nucleophile has minimum hindrance from the groups which are attached to carbon. And thus, the order of reactivity would be methyl halides. We put it like this: CH3X greater than R, CH2X greater than R2CHX greater than R3CX, which means that the order is like methyl halide greater than primary halide greater than secondary halide greater than tertiary halide. So I think methyl and primary halides, they exclusively undergo SN2 in substitution reaction, whereas secondary halide, there would be SN1 and SN2 both possible. We're not talking about SNAR, which is meant for only aromatic systems, and SNI, which is for very special reactions. So here we would be comparing SN1 primarily with SN2 because these are the two most commonly known substitution reactions. So when we talk about SN2 reaction for secondary halide, I may say, yeah, secondary halides, SN2 is possible, but then SN1 would also be possible. However, with methyl halide and primary halides, it is, SN2 which is most preferred. And there would be no or very, very less SN1. So basically, you have to know this. Coming back to probably, admitting Nirali because she went off. I was searching for this, yeah. So basically, coming back to you now, so order of reactivity is here. So after having done all this, there are a few things that you have to know, things which go beyond the textbooks, but you have to know them properly. So I am going to talk about a few things which are more than your, normal textbook. Yeah. So let us go to the next part. Suppose if I have to know which reactions or which which reactants can preferably undergo SN2 reaction, then you would say methyl halides as well as primary alkyl halides. That's correct. But there are some other components which may also show SN2, and there are several reasons for it. Now let us understand the basics. It says that SN2 reaction can occur. SN2 reaction can occur only if this transition state is more stabilized. Because if this transition state remains highly unstable, then the first step itself would not take place. It would get reversed and you will not have any transition state formed. So it is very important that the transition state here is, stabilized properly. So any such substrate in which the transition state here gets more stabilized is going to be, undergoing SN2 preferably. So the key to any substrate showing SN2 reaction is that it should form a very stable transition state. Now, what makes this transition state very stable? Let us understand that. Stabilization of transition state would depend on how easy it is for this carbon to shift the electron density that it has around it onto other atoms. So if it is possible for this carbon to shift some of its electron density onto any one of the surrounding atoms, then it can offload some of the electron density from it. And when this happens, the transition state would be more stable. In general, if this carbon is able to lose some of its electron density to some surrounding atoms, then the transition state would automatically become more stable. A carbon પરથી electron density ઓછી થવી જોઈએ તો transition state stable થાય. Is it okay? So now let us figure out how this can be done. So I would be giving you a list of some very special substrates, some very special reactants where this happens. And they all have a tendency to show SN2. Okay, so let us go to that. The first category of substrate. Any substrate which has, a pi bond in beta position. Now, what is a pi bond in beta position? You know, this is the alpha carbon, the carbon which is connected to halogen, and this is the beta carbon. We call this as, you know, having a pi bond here, we call this as beta unsaturation. So this is your beta unsaturation. So what can happen if you have beta unsaturation? SN2 is preferred. Why? I would show you. This is your nucleophile, right? And this nucleophile is attacking your positive carbon, right? Let us find out what kind of transition state gets formed. So we put it like this: CH2, CH. I'm just drawing the pi bond. All right. This is C. H2 remains as it is. The two hydrogens here, they are here. This is the outgoing or the leaving halogen, and this is the incoming nucleophile. The carbon has become pentavalent and there is a huge electron density around it. However, if you have beta unsaturation, the pi orbitals, they can actually accommodate a fraction of electron density into them. Although they already have some bonds, so, you know, some electrons, I'm sorry, they have 2 electrons, but still there is enough room for, you know, some electron density to be accommodated here. This would offload the carbon of its electron density to a certain extent, and hence the transition state is stabilized. So we say this is vinyl halide, right? This is vinyl halide. So we say substrates like vinyl halide, they can show SN2 because they have beta unsaturation. With beta unsaturation, the pentavalent carbon, this carbon is called pentavalent carbon, right? The pentavalent carbon can lose some of the electron density into the pi orbitals in beta position, and hence it can stabilize itself, and that is the reason why it can show SN2. A similar situation is with benzyl halides. So when you take up a benzyl halide, there is a very similar situation. Look at this. The leaving group of benzyl halide and the incoming nucleophile. You can see that this is your alpha carbon and this is your beta carbon, and this is where your electron density is supposed to go. So you find that some of the electron density can move into the pi shell, and that stabilizes the entire structure. So benzyl halides and vinyl halides show benzyl halides and vinyl halides. Allyl halides, right? They give SN2. They do give SN2, although our book would never give this, but yes, they do give SN2 as per, you know, so see, such questions are given in competitive exams, and you should not think about how is benzyl or, you know, I'm sorry, I've written vinyl, I'm extremely sorry. This is allyl, sorry. So they do ask questions wherein allyl halides and benzyl halides are supposed to show SN2 reaction. Yes, they do give. That's because the transition state or the pentavalent carbon can release some of the electron density into the beta, you know, pi orbitals, and that is how it stabilizes itself. Okay, so this is something which you have to know. The first case, coming back to you, there's one chat box. Okay, RDS. Kalp, RDS is rate determining step, a step which decides how fast the reaction would take place. Okay, so RDS is rate determining step. Okay, Kalp, I hope you've understood that. That step decides how fast the reaction would take place. Okay. Yeah, going back to, once again, we've lost one member. Again, the net issues. So going back to this, so this was the first case. The second case that you have to know here, where SN2 can exclusively take place or highly preferred, is a case where you find that there is a heteroatom connected to alpha carbon of any halide. So this is your alpha carbon and this is your heteroatom. Heteroatom generally should have at least one lone pair. So I can put this, one of the lone pairs I can show in form of an orbital with 2 electrons. Now, what would happen when you have a nucleophile attacking this? Let us draw the transition state. The transition state would go like this: CH3O, and then we have this CH2. This is, let's say, X, and this is, let's say, Nu. Now, oxygen being electronegative can vigorously pull these electrons and accommodate a fair amount of electron density from carbon into its non-bonding electron. Non-bonding orbitals, I'm sorry. So oxygen being electronegative, it can very easily, pull this electron density into its non-bonding orbital. Thus, it can decrease the electron density on this pentavalent carbon to a very large extent, and hence such a transition state would be highly stabilized. And we find that when you have a heteroatom in alpha connected to the alpha carbon, there is a huge possibility of SN2. So this is like offloading, carbon offloading some of its electron density into the non-bonding orbital of heteroatom. So again, the third condition where this can happen is when your alpha carbon has any heteroatom directly connected to it. More electronegative this heteroatom, greater would be the pulling. Greater the pulling, more stable the transition state. More stable the transition state, greater is the possibility of SN2. And then there is one more. This was like, this was the first possibility. This was the second possibility. And now we have the third possibility. Third possibility is, a possibility where only SN2 occurs. When you have, okay, just a moment, Yashvi. Yeah. So when you have a carbonyl group, this is a carbonyl group in beta position to, it can be anything here. This is the alpha carbon and this is your beta. Such molecules, we say substrates with beta carbonyl groups. We call them as alkyl halides with beta carbonyl. Now, when you have a nucleophile attacking here, you find that this R, C double bond O, C, H, H, and there is this nucleophile. Now what happens is, because oxygen is quite electronegative, it would pull electrons towards it, making the orbital of carbon almost empty. And because this carbon has an empty orbital and a very strong positive charge, you find that it can very, very strongly pull the electrons, right? This is exclusively SN2. Avu kahi hoy to exclusively SN2. एक ज मिनट में થઈ જાય SN2 reaction, right? So beta carbonyl group, only SN2. What would happen if you have your benzyl halide? Suppose I'm talking about the fourth thing. What would happen if your benzyl halide, which is supposed to undergo SN2, has some electron withdrawing groups here? What would happen to its capacity of showing SN2, right? What would happen to its tendency to show SN2? It will show enhanced tendency, to exhibit SN2. It will have enhanced tendency to exhibit SN2. Remember this, right? Why? Because electron withdrawing groups can pull electrons towards them. So what would happen if they start pulling electrons towards them? If they start pulling electrons towards them, this carbon, which is going to be pentavalent in transition state, would lose electron density to these electron withdrawing groups, and hence SN2 is highly favored. So putting electron withdrawing groups on the ring would increase the tendency of showing SN2. On the other hand, if I put electron donating groups, groups which give electron density to this carbon would become even more negative, and electron density on this carbon would increase. So if I put electron donating groups here on the ring, the electron donating groups would push electron density onto this carbon, making the transition state even more unstable. So electron donating groups decrease the tendency of SN2 reaction, and electron withdrawing groups increase the tendency of SN2 reaction. I hope you have understood this. And then there are certain substrates which do not give SN2 at all. So there are certain substrates, in fact, they don't give substitution at all. Aryl halides. Why? Because they have the lone pairs in conjugation with pi bond. So a partial double bond character is generated at this point. The bond doesn't break. Then we have this vinyl halides. Again, the same thing. Due to resonance, a partial double bond character generated. Bonds are very difficult to break. So aryl halides, vinyl halides, and even the bridged structures where a pentavalent state, this is a bridged carbon, a bridged hydrocarbon, and a pentavalent state at bridge structure or a bridge carbon would be extremely destabilizing. So we call this as bridged halides. These are the three components. They cannot undergo substitution reactions. So when I say, these are the three components which may not easily undergo substitution. This is the fifth point. below given substrates cannot give SN2 or even any other substitution reaction, but because I'm doing SN2 here, I may say they don't give SN2, okay? So this is in general, you always have some exceptions, but this is in general observed, right? The five, different five different substrates, where SN2 can take place. Some of them where SN2 cannot take place. I have given you all of it. You just have to go through it and understand it. In my notes, I have written everything, every bit of it. So now if you have any doubts, I can come back to you for asking your doubts. Sir, મારે ફિઝિક્સના ક્લાસ 3:30 છે. લેક્ચર કેટલા વાગે પછી પતી ગયું છે બેટા? I am done. Huh? I am done, Bala. So I think all of y'all, if you have any doubts, you can go through the notes and ask me if you have any doubts. As of now, I have to say goodbye, and we meet next time in your regular class. This is recorded, and so I can give you a link, and you can revise this lecture again and again. I would be sending you the link today itself on WhatsApp. So all those of you who have missed or want to revise it again, I would send the link. You can do that. Okay. Thank you very much. We end this meeting. Bye, everyone.